Today we're going to talk about arc length and curvature, and probably also in the title of this section should be the Frenet frame, the TNB coordinate system. There's a lot here. It's going to be an adventure. This will probably be a long video. I've got a couple of fun sort of excerpts in here. There's a nice animation of Frenet frames that I'll include, and I'll also kind of connect it to the idea of sending space probes out into deep space, which is very closely related to space curves that we're studying now, and the Frenet frame, etc. What are the big takeaways here? What are the goals? I want you to be able to integrate space curves in order to compute their lengths. I want you to be able to compute and understand the curvature of a space curve and kind of relate it to the sharpness with which it bends. And finally, I'm going to introduce we've already got the unit tangent vector. I'm going to introduce the unit normal vector and the unit binormal vector. And then the three of them together form a little tiny orthogonal coordinate system for every point along the space curve. We'll see that in a second. So computing arc length, we're going to see that it's really just a sum of small displacements computed as the speed along the curve times a small time, dt, and I've got a little bit of a typo here. This should say a small time, dt. Because remember, speed has units of, say, meters per second, and time, of course, might have units of second. And when you multiply them together, what you get are meters. And with this integral, we're able to sum up lots and lots and lots of tiny little length segments along the curve to compute the length of some piece of the curve. Related, we're going to talk about the arc length parameterization of a curve. And this is a different way of specifying a location on the curve. Up until this point, to specify a location on a curve, we've been giving just the t parameter t, and we don't really, t we've been imagining as being time. So, okay, go to the curve at time 10, whatever that means. A more natural way of locating places on curves is actually to pick a starting point and then say, go 10 miles down the curve. That's the location I care about. Or go 40 feet down the curve. And if you think about it, that's exactly how we mark locations on our highways. We pick a starting location, perhaps, I don't know, imagine that you're driving along Interstate 90 and you hit the Washington-Idaho border. At that point, the mile markers reset to 0. And as you continue along 90, you see mile marker 1, mile marker 2, into Idaho. So if I'm in a car accident, what I'm going to say is I'm in Idaho on Interstate 90 at mile marker 4. And then emergency services are going to know, okay, I'm going to get on the highway and I'm going to go to mile marker 4. And that 4 actually has meaning. It says you're actually 4 miles from the Idaho-Washington border along the highway. That turns out to be a mathematically very useful thing to know, and so we'll talk a little bit about arc length parameterization and how to take a curve that's not arc length parameterization and convert it to one that is arc length parameterization. Finally, I'll introduce the Frenet frame, the TNB frame, and we'll talk about osculating planes and osculating circles. Let's do a quick flyover of the book, and then we'll get into the examples. We are in section 3. Here are some of the objectives. Let me just remind you, or sort of talk a little bit about the arc length formula. When you have a trajectory r, or a space curve r, and you compute the magnitude of r prime, what you're actually computing is the speed at time t. If I want to kind of figure out the length along the curve, what I can do is take these little speeds, the speed at time t times the sort of delta t at time t, and just sum them up along the length of, along that chunk, t equals a to t equals b, and what I get is the length of the curve along that section. It turns out whether you're in 2 dimensions or 3 dimensions, that looks exactly the same. And while we have these larger expressions in terms of the component functions f, g, and h in 3 dimensions, I want you to focus on this and understand that computing this quantity, the magnitude of r prime, is really your goal when you're doing an arc length formula. Computing the arc length, let me just walk you through this quick example. So in the first case, let's do the second case. We've got a three-dimensional vector, three-dimensional space curve, t cosine t sine t, and 2t along the segment from 0 to 2 pi. So we want to compute how long is that little piece of thread. So if you took that out of the space curve and stretched it out, not pulling, but just sort of laying it out straight, how long would it be? Of course, first steps are to compute r prime and then the magnitude of r prime. And if you do that, you do the component-wise derivative here, and then you take the sum of the squares of the components and the square root. You put that underneath the integral sign, and usually these are pretty challenging integrals. I will say that most of the exercises that you're expected to do by hand in the text and for homework are carefully crafted to work out nicely. So if you're ending up in a place that seems like a total train wreck, chances are you've made an algebra mistake. You might want to jump over to Sage and check some of the intermediate steps, like computing r prime with Sage and computing the magnitude of r prime. And we'll do an example of that later. In this case, you compute the magnitude of r prime. It turns into this. Often there are some nice trigonometric identities that you can take advantage of, at least when you're dealing with a trig trajectory. And it boils down to something like this. Even this is not an easy integral. This integral involves an integration formula, or if you want to dig into it, it's probably going to involve some kind of trig substitution. You can go look that up, or you can go plug it into Wolfram Alpha, and you end up with this result, pretty messy, but as a decimal somewhere around 25 units long. I think this is a good illustration of the challenges of computing arc length. These are typically messy expressions and challenging to integrate. So most of the time in practice, you're actually using a computer to compute these. Let's keep going. Here's another example of doing arc length. Once you have arc length in your pocket, then it's useful to think about the arc length function. And this is akin to, again, going back to the earlier example of crossing the Washington-Idaho border on Interstate 90. You're heading into Idaho, and the mile marker resets at 0. We're going to call that sort of our A. That's where we're starting, is the border. And what we're going to do is we're going to build this integral that has the magnitude of r prime as its integrand, and we're going to integrate from some arbitrary starting point A out to t, and we're going to call that a function. And the beautiful thing about this function is what it's telling me is the distance that you've traveled up to this point t, time, is blah. And once you have that, some beautiful mathematics starts to occur. For example, the derivative of this function is really just the speed of the space curve at a particular time. So the derivative of s of t at time t is just the magnitude of r prime of t. That makes arc length parameterization useful. Typically what you do is you compute s of t, and if you want to take your original space curve that is just expressed in terms of t, and you want to re-express it in terms of s, all you have to do is solve for t in terms of s and substitute that into your original arc length function, and suddenly it's got arc length parameterization, which we like. So here's a formal definition of the arc length function. Again, you pick some arbitrary starting point as the lower limit of integration, and then you have a variable as the upper limit of integration. And then remember that your dummy variable now can't be t, because you have t appearing as a limit of integration. So just to be safe, you should change it to some other letter, and here we're using u. The arc length function is defined like this. And then if you want to do sort of reparameterize, or as the book says, find an alternate parameterization of a given curve, you can follow this example. Let's do problem A and just quickly follow the example in problem A. The first thing to do is to compute s of t. And again, all of the exercises that you'll be asked to do by hand in the textbook and for homework are going to work out nicely, but these can also be extremely challenging in real life. So you compute s of t. How do you do that? You compute the magnitude of r prime, you do the integral, and you end up s of t is equal to 4t. If you solve for t in terms of s, you find that t is equal to s over 4. That's an easy algebraic problem. Just divide both sides by 4. And then to reparameterize in terms of arc length, you take the original space curve up here and you just replace t with s over 4. This is going to describe the same curve, the same shape, but now it's parameterized by arc length. This has useful theoretical properties as well as actual application, and so I'm going to expect you to be able to do that kind of reparameterization. Okay, next on the agenda is the curvature. The curvature is a way of measuring how sharply a curve is bending at any particular moment. And in the figure here, we see at this point, the curve is bending not quite as sharply as, say, the curve over here. And what we do is we use circles to kind of measure the bend. We'll say that the arc of a circle is kind of the canonical curvature idea. And the bigger the circle that you can fit, sort of tuck snugly into the curve at this point, the lower the curvature. Alternatively, the smaller the circle, the higher the curvature. And actually, what happens is curvature is inversely proportional or inversely related to that little nestled-in circle. This nestled-in circle is called the osculating circle, and it has a very specific meaning, which we'll talk about in a minute. The definition, the formal definition of curvature is given by, well, if t is given, let me back up, if r is given in terms of arc length, like an interstate highway, for example, then you can compute t as just the derivative of r with respect to s, and the curvature is the magnitude of that derivative. So curvature is a scalar, and don't make a mistake here, this is not a lowercase k, this is a lowercase kappa. Now, most of the time we're not given our curves in terms of arc length in math class. We're typically given them in terms of some arbitrary parameter t. And if you want to use this formula, of course, it requires that the curve be given in terms of arc length. Reparameterizing, as we saw earlier, can be a bit of a challenge. So wouldn't it be nice to be able to compute curvature without needing an arc length parameterized curve? The answer is, of course, yes. And so let's show an alternate formula for doing that. An alternate formula, there's several alternate formulas given here. The one I want you to focus on is this middle formula. The middle formula is beautiful because if you're given a space curve r of t, you can compute r prime of t quite easily and r double prime of t quite easily. Also, there's a bit of a typo here in the book, or a rendering issue. This is just r double prime, the second derivative of r with respect to t. So back to computing curvature, you compute r prime, you compute r double prime, you compute the cross product, you compute the magnitude of r prime, you cube it, you form this ratio, and you've got kappa, and that sounds like a freaking nightmare, I got you. But it's actually going to be better than reparameterizing the curve in terms of s. Sometimes this is just impossible, whereas this is generally always possible to do. So I would encourage you to really focus your attention on this curvature formula. The other two, really not so much. Even this one, when I'm given a function y equals f of x, what I usually do is write the space curve for it, r of t, and then I just jump up to this thing here. The proof of these formulas follows from the original definition of the curvature as the derivative of t with respect to arc length. And you can kind of chase it down, but the first thing we note here is we can get dt dt as dt ds times ds dt using the chain rule. We can find the magnitude of dt ds, which we know to be the curvature, as just the magnitude of t prime with respect to t over ds dt. All right, how did that happen? We took the magnitude of both sides and we divided by ds dt. So we solved for the magnitude of this. And we know that dSdt is actually the magnitude of r prime of t. So we get this, and that's the first curvature formula. That's easy enough. Now, if you carry this out a little bit more, if you look at this identity, that this is the definition of the unit tangent vector, and you differentiate with respect to t, it's a bit of a mess. There's product rule, yada, yada, yada. But if you chase it through carefully, what pops out is this identity right here. And then if you take the magnitude of both sides of this identity, and note that since t prime is parallel to n, t is orthogonal to n, and it follows from the cross product identity for magnitudes that the magnitude of t cross t prime is actually just the magnitude of t prime, because t is a unit vector and the angle between them is pi over 2. So you get this really beautiful identity that the magnitude of t cross t prime is really just the magnitude of t prime. And we can take that and take the magnitude of both sides of this equation, and on the right-hand side you get the magnitude of this, because this is just a scalar. It comes out of the magnitude calculation. What's left behind is this thing, which follows from this identity over here. And then there's another typo, or a typo in the text here. This also should have magnitude bars around it on the left-hand side. So this is the magnitude of r prime cross r double prime equals this expression. And then we solve for this expression right here. And then finally we divide by another factor of magnitude of r prime, and we end up with the familiar cross product formula, the one that I really want you to focus on. And then last, if your curve is given as a function y equals f of x, you can simply chase that down in this formula and end up with the familiar formula that you may have learned in Calc 1, I guess. Yeah. So once again, I really want you to focus on this middle formula. That's a really helpful tool. And then the other ones, if I want you to work with the other ones, I'll remind you what the formulas are. All right, let's carry on. I'm not going to go through finding curvature here. I have a couple of examples at the end that I'll talk about. Again, this is a really long chapter, or sorry, section, and there are a lot of different topics that I want to try to hit in a finite amount of time. All right, next on the agenda, we already have a definition for the unit tangent vector. That's just r prime over the magnitude of r prime. We're now going to define two new vectors, the unit normal vector, which we define to be t prime divided by the magnitude of t prime. We start to see a pattern here. And then the binormal vector is simply the cross product of t with n, the unit tangent with the unit normal vector. It's important that you know that the binormal vector is defined as t cross n, not n cross t. So remember that cross products are not commutative. You can't switch them. Or if you do, you're going to introduce a minus sign. So the binormal vector you have to memorize. It's t cross n, not n cross t. And the normal vector also memorize. It's t prime over the magnitude of t prime. This is a unit normal vector. And what's really interesting about these three vectors, and by three vectors I'm talking about t, n, and b, t was introduced in the previous section, is they form a tiny little orthogonal coordinate system at every point on the curve. And this is quite useful in lots of applications. Let me show you what that orthogonal coordinate system looks like. It's called a Frenet frame, first of all. Actually, you know what, before I do that, let's do a quick calculation here. Let's look at computing the unit normal vector and the binormal vector for, say, part B, this 6t plus 2, 5t squared minus 8. Okay, carrying down, here we've got this curve. All right, you want to find the unit normal vector, sorry, the unit tangent vector first, and that's just r prime of t over the magnitude of r prime of t. And you can see these are messy calculations. Next, we want to compute t prime and the magnitude of t prime, and again, this is going to be work. To compute t prime, we've got to compute the derivatives of each of these, which is going to be messy. And then to compute the magnitude of t prime, you've got to square them up, add them up, take the square root. This is a medium difficult problem, but it still kind of works out. We find that the magnitude of t prime is just this, and then to get n, we take t prime divided by the magnitude of t prime, and we get something that looks like this. Observe that t and n are orthogonal. That's a quick way of checking if your calculation is correct. T dot n is orthogonal. T points along the curve, and n points perpendicular to the curve. And then finally, B is T cross N, and here you see the authors using the familiar determinant approach to computing the binormal vector. And brilliantly, this binormal vector simplifies dramatically. So here you have the tangent vector along the curve, you've got the normal vector along the curve, and finally you've got the binormal vector along the curve. And remember the right-hand rule. Put my fingers in the direction of the tangent vector, palm towards the normal vector, thumb goes in the direction of the binormal vector. So it's a right-handed, tiny little coordinate system, T and B. How do we interpret n maybe more physically? If I am going along a space curve like this, right, the tangent vector is kind of tracking along tangent to the curve. What the unit normal vector is telling me is which way the tip of the tangent vector is about to go at this moment. So if I have a sort of a curve going like this, we can expect the normal vector to be pointing in the direction that the tip is about to go, like this. So that's how we decide between this direction as normal and this direction as normal. It's always pointing into the curve as opposed to out of the curve. So remember that. The unit normal vector is always pointing into the turn perpendicular to t. And then the binormal vector is just the cross product of the two, and you can figure out its direction by the right-hand rule. Together, those are called the Frenet frame. This static image really doesn't do it justice, so what I thought I would do is share with you a visualization of the Frenet frame. And let me get this little app started. So here we see an animation of the three vectors, the tangent, the normal, and the binormal vectors. And you're like, hey, Schuler, what's happening here? It's just sort of floating around in black space. Let me turn on the curve, and you can see that it's following this curve in space. Now that we see the curve, we begin to understand which are which. Can you look at the three vectors and figure out which is the tangent vector, which is the normal vector, and which is the binormal vector? You could pause and think about it a little bit here. Okay, hopefully you figured that out. You can see that the yellow vector is definitely pointing along the curve. And as it sweeps through, for me, I feel like back here is kind of where I really can tell the difference between the normal and the binormal. It's along this sweep. It's really hard to see what's going on here, but one thing you should note is, or recall, is that the normal vector is always sort of telling you which way the tip of the tangent vector is about to bend. And we can see as we're traveling along this section of the curve that the tip is about to bend in this direction. That tells me what the normal vector is. And again, if I kind of advance this slowly, I can see how that's happening. Now imagine the binormal. Put your fingers along the yellow tangent vector, your palm towards the turquoise normal vector, and your thumb is going to point along the purple binormal vector. As this Frenet frame travels through space, at each point you get a different set or a different trio of vectors. And you get this little miniature coordinate system. Let me let's kind of pause it right here, and I can give you a little bit of intuition about the purple vector. You see how the whole frame is kind of twisting as it travels through this section? That's something that's not at all obvious as you go through it, and that's what the purple vector tells me. So the purple vector does for the turquoise vector what the turquoise vector does for the yellow vector. In other words, the purple vector, the binormal vector, is telling me which way the tip of the turquoise vector, the normal vector, is about to bend. And we can see that it's about to bend, as I advance this, it's about to bend in this direction, and that's what the purple vector is telling me. And as I step, you can kind of see that. Because this normal vector, the turquoise vector, is perpendicular to the curve, the purple vector is kind of measuring how much this particle is twisting around its trajectory as it travels through space. So if this were some kind of spacecraft, the purple vector would kind of tell me how the spacecraft is twisting as it's traveling along the curve. And hence, the binormal vector is actually closely related to something called torsion, which we won't study here, but people that, for example, study spacecraft and things floating through space might study. And as an example of that, I've pulled up a simple animation of the two Voyager space probes as they leave Earth and head out into deep space. This is a somewhat long video. I mean, it's 2 minutes, and the early part is kind of boring, but it does set you up for some really interesting stuff later as the probes interact with some of the planets in the outer system. You should know that engineers and aerospace engineers use planets to accelerate their space probes so that they don't have to carry as much fuel. And you can see two beautiful examples of this, or several beautiful examples of this, with the Voyager 1 and Voyager 2 spacecrafts as they head out into deep space. And in fact, you can see the engineers using the gravitational pull of these large outer planets to actually not only accelerate the probe, but change its direction. So here we go. So we're focusing on the Voyager 2, and as this progresses, you'll start to see Voyager 1 appear. Apologies for the stuttering. You know, maybe full screen is a little bit too much, so let me back off and go to the smaller screen. See if that does any better. All right. It's not super great, but we'll just kind of talk through it here. If you don't know, Voyager 1 and Voyager 2 were two of the earliest deep space probes that NASA launched. And they did a couple of flybys of some of the outer planets of the solar system. And of course, they never came back. They just kept going. And these two objects, these two space probes, are now, there's Voyager 1 interacting with Jupiter. And boy, it takes a hard turn using Jupiter. And then Voyager 2, a little bit later in that same orbit, connects with Jupiter and goes. Now Voyager hits Saturn and uses Saturn not only to accelerate, but to leave the plane of the solar system, whereas Voyager 2 uses Saturn to just make another sharp turn and accelerate. Now Voyager 2 is going to keep going. Voyager 1 is going up above the plane of the solar system, and now Voyager 2 hits Neptune and is going down below the plane of the solar system. So despite the really shaky video, you can kind of see how these space curves might be useful, and these Frenet frames might be useful as we sort of develop trajectories for deep space probes. Each of those probes has a little Frenet frame associated with it, a tangent vector, a normal vector, and a binormal vector. And there you have it. All right. Now, one last big idea, lots of big ideas here, I recognize that. I want you to look at N and T here, and imagine that N and T, along with the point that they're situated at on the curve, those three entities together define a plane that is tangent to the curve at that point. That plane is so useful that it actually gets its own name. That plane is called the osculating plane. And there's a circle that sits in that osculating plane. So imagine here's another trajectory. Here's the unit tangent direction. Here's the unit normal direction. Here's the point P. Right? We know back from the lines and planes section how to create a plane that goes through that point and is parallel to these two vectors, right? We take the cross product, we get the normal vector, we get the point, we write the equation of the plane. It's great. Now, if you take the circle that sits in the osculating plane that has radius that matches the curvature, radius that matches 1 over the curvature, and whose center lies along the normal direction in the osculating plane, you get something called the osculating circle. Why is this useful? This provides a beautiful approximation of the curve at this point. You can see for this simple curve that the curve and the osculating circle are nearly indistinguishable for very long stretches before and after P. So the osculating circle is a fantastic approximation of perhaps a complicated curve at that location. I'll leave you with a little bit of trivia before we go on. Where does the word osculating come from? If you translate the word kiss, translate kiss into Latin, the first hit is this word basium, but the second hit down here is osculum. So a kiss in Latin is an osculum. And you can see this root here, oscule, is exactly the same root that we have in both osculating circle and osculating plane, because the osculating circle kisses the curve at the point P, and similarly the osculating plane kisses. It's another word for tangent, really. Finding the equation of the osculating circle involves a couple of steps. You want to find the curvature of the osculating circle, and then you also have to find the normal direction at the point. So here we find the curvature using the y equals f of x formula, and then we also, we just kind of note here, they're interested in the curvature at x equals 1, which is this point here. And they note that perhaps with not great, actually no, they have some good justification here. The unit tangent along the curve here is horizontal. That means the unit normal is perpendicular to the, we know the unit normal is perpendicular to the unit tangent, so the unit normal is going to point parallel to the y-axis. We also know that the unit normal is pointing into the curve, so it's pointing in the positive y direction. So if we compute the curvature, and we know that the radius of the osculating circle is 1 over the curvature, we actually have enough information to write the equation of the osculating circle. We know that given the curvature, the radius of the osculating circle is 1 over the curvature, so we go a distance 1 over the curvature in the direction n, which is going to define the center. Once we know the center and the radius, we can quickly write the equation of the circle using the standard form. And we end up with this equation, and that corresponds to this tiny little osculating circle. It's tiny because the curve is bending quickly here. If we were to build the osculating circle out here at, say, x equals 2, we would have a giant circle because the curve is nearly straight. And you can imagine building the osculating circle on a straight line is impossible because the curvature is 0, the radius is infinite. We'll do an example of that in the exercises, which are about to begin right now. Okay, let's talk a little bit about the first exercise, problem 104. I've got these over in my notes here. So in problem 104, you're asked to compute the arc length of this particular chunk. The visual here is just a sketch of this curve over the segment 0 to pi. Remember that arc length is always just the integral over the parameter range t. So here we're going to do the integral from, what's the parameter range? 0 to pi. And we need to compute r prime. R prime is simply 2 cosine t, and then 5 in the middle, and then minus 2 sine t. And then we need to compute the magnitude of r prime. And that's going to be the square root of the sum of the squares. So 4 cosine squared t plus 25 plus 4 sine squared t. And I will say, again, when you're doing book exercises, they're usually built to work out nicely, and we can see that things are working out nicely. I'll use my rainbow pen here to emphasize that we've got a 4 cosine squared and a 4 sine squared. That's going to collapse into just a 4 using the Pythagorean identity. And then 4 plus 25 is 29, and we end up with root 29. You know, not the most beautiful number in the world, but I've seen worse. Square root of 29. All right, what am I supposed to do with that? Well, remember that the arc length is the integral over the specified parameter range, 0 to pi, of the magnitude of r prime. Well, we just calculated that. That's the integral from 0 to pi of the square root of 29 dt. We can integrate a constant with respect to time. That's one of the easier ones. So we have root 29 times t, and we want to evaluate from 0 to pi. Plugging in pi, plugging in 0, and subtracting, we end up with pi root 29. So that's a nice warm-up, get us used to this idea of computing arc length. In problem 110, you're only asked to set up the integral and not actually evaluate it. And I'll do that also sometimes in other homework and evaluations. Setting up the integral is really important because if you can set it up properly, you can often jump over to a computer algebra system like Sage or Wolfram Alpha to actually do the calculation. So we're going to set up an integral to find the circumference of the ellipse with this equation. Well, circumference for us, remember, that's just the length around some figure in the plane. This is an ellipse in the plane. So let's think about how we would compute its circumference. We see that this thing is going out about 1 unit, precisely 1 unit in the x direction, and maybe 2 units in the y direction. I can just tell that from the parameterization because there's a 1 here and a 2 here. So 1 in the x direction, 2 in the y direction. And we can sketch in the rest of the ellipse. All right. We want to figure out how long. If this were a piece of thread and I laid it out straight, how long would it be? That's the arc length. Well, in this parameterization, how do we go one complete traversal of the ellipse? Well, think about it a little bit. If you're here at the point 2, 0, that corresponds to t equals 0. I'm sorry, 1, 0. That corresponds to t equals 0. Up here, you're at 0, 2, and that corresponds to t equals pi over 2. And if you keep going out here, this is t equals pi. This is t equals 3 pi over 2. And then finally, you're back at the beginning. You've gone around exactly once. You don't want to have too short of a parameter range because then you're not going to have the full circumference. And you certainly don't want to have it too long because then you're going to count parts of the curve twice or more, and that's not good either. So one traversal corresponds to the parameter range 0 less than or equal to t less than or equal to 2 pi. So it's important to figure out what the parameter range is if we're going to compute the correct arc length. All right, so we figured out the parameter range. Let's compute r prime because we know that we need the magnitude of r prime. R prime is just the derivative component-wise, so minus sine t, 2 cosine t, and 0 in the last slot. So this curve is sitting in the xy plane. There's no k component. The magnitude of r prime is the square root of sine squared t plus 4 cosine squared t plus 0, like that. Now, you can't get carried away with Pythagorean identity. I could pull out my rainbow pen here and underline these, but it's not going to help. I don't have a 4 here, right? And so I cannot apply the Pythagorean identity. I'm just stuck with this particular expression. So the length, or the circumference, which we'll call c, is the integral from 0 to 2 pi, the full parameter range of the magnitude of r prime, in this case sine squared t plus 4 cosine squared t square root dt. That's a hard integral. Luckily, you only had to set it up, right? You didn't have to do it. So we've set it up, we're done. If we want to figure out what the circumference is, we could go over to Wolfram Alpha, or we could start grinding away with perhaps some sophisticated integration techniques. All right, in problem 118, we're given this trajectory, and we're asked to find the unit normal vector. This is going to be a bit of a challenge. There's some work here, and I want to show you that you can't really shy away from the work. When I'm asking you to do these things by hand, I want you to grind it out. So to find the unit normal vector, we first need to find the unit tangent vector. We need to find t, and we'll recall that t is the magnitude of r prime. Sorry, it's r prime over the magnitude of r prime. So we've got to do some of that work first. R, I'm going to rewrite r in a slightly different way that will be advantageous to us. I'm going to factor the common factor of e to the t out of each component. And what we have left behind is 2, comma, cosine t, comma, sine t. To take the derivative, you may recall from the differentiation section just previously that there's a a product rule associated with things that look like this. And I can take the first times the derivative of the second plus the second times the derivative of the first. Well, the derivative of the first is e to the t, and the second is just 2 cosine t sine t, like that. That's a little bit easier maybe than computing the derivative of the original expression. I'm going to simplify this a wee bit. I can factor, again, e to the t out front, and then add component-wise. So I have 2, and then I have minus sine t plus cosine t, and then cosine t plus sine t. All right, now I have to take the magnitude. Once again, we can take advantage of some identities that we know about magnitudes. If we have a scalar function times a vector, then the magnitude of that vector is the absolute value of the scalar function times the magnitude of the vector, which is 4, plus, gotta kind of multiply it out here, sine squared t minus 2 sine t cosine t plus cosine squared t That's what I get by multiplying out the middle, or the j component. And now let's multiply out the z component. That's cosine squared t plus 2 sine t cosine t plus sine squared t. And all of that is square root. There is some nice simplification that occurs here. We get rid of these cross terms, thankfully. We have a cosine squared, so let me get out my rainbow pen. We have a cosine squared here and a trying to be fancy. Okay, cosine squared. So let's see how things clean up here a little bit. We have a cosine squared and a sine squared here, which turn into 1, and a cosine squared and a sine squared here, which turn into 1. When it's all said and done, of course, the absolute value of e to the t is just e to the t, because the exponential function is always positive. And underneath the square root, we have a 6. So as frightening as this seemed originally, this actually simplifies rather nicely. T is now r prime divided by the magnitude of r prime, which we've just computed. And notice the magnitude of r prime has this component, and r prime itself has this factor. So when we divide r prime by the magnitude of r prime, those are going to cancel. And RT turns out to be a relatively nice expression. It's 1 over root 6. I'll keep that outside. 0 minus sine t cosine t. So there's a calculation that I would expect you to be able to do. That said, we're not at the unit normal vector. Recall that the unit normal vector, n, is equal to t prime over the magnitude of t prime, so we've got to do all of that again. Let's hope it's not as bad. T prime is the derivative of this guy with respect to t. The 1 over root 6 is going to go along for the ride. The derivative of the first component is 0. The second component, cosine t. The third component, minus sine t. Now we need to find the magnitude of t prime. That's going to be 1 over root 6, because remember that scalars just pass through magnitudes. 0 squared plus cosine squared t plus sine squared t, yay, square root, and the magnitude is simply 1 over root 6, and the unit normal vector is now just t prime divided by the magnitude of t prime, which yields that vector. Notice that's a unit vector. You might also notice that it is orthogonal to t. How can we see that? Again, that's not part of the problem, but notice that t dotted with n is equal to 0. Just carry out that dot product and you'll see that. You could also compute b if you wanted to. You could do b is equal to t cross n. I'll leave that to you as an exercise. All right, problem 126. I don't know why these are kind of reversed, actually, because here we're asked to find the unit normal vector, and along the way we had to find the unit tangent vector. Here we're just asked to find the unit tangent vector. Mostly I just want to do this to give us some practice for finding t. All right, so t here, recall that t is r prime over the magnitude of r prime, so we've got to start computing all the bits. R prime is 2 cosine t, 5, and minus 2 sine t, and the magnitude of r prime is 4 cosine squared t plus 25 plus 4 sine squared t square root. Another Pythagorean identity coming to our rescue here, and we get the square root of 29. So the magnitude of r prime is just root 29, and t is r prime divided by root 29. So 1 over root 29, 2 cosine t, 5 minus 2 sine t. And there's our unit tangent vector. You might want to practice a little bit and go on and try to compute n. Not sure if it works out nicely, but you could give it a shot. Okay, in 132, we're asked to find the curvature of the given curve. The curve, notice, is given in terms of t. So let's walk through finding, and recall that the curvature formula for curves given in terms of t is kappa magnitude r prime cross r double prime over the magnitude of r prime cubed. So let's compute all of these various constituencies and put them together to compute kappa. R prime is simply minus 5 sine t, 5 cosine t, and 0. R double prime, again, we have to include this third component, even though the original curve might be just considered two-dimensional, because we're going to do a cross product, and the cross product only works on three-dimensional vectors. R double prime, we'll take the derivative of this thing again, minus 5 cosine t, minus 5 sine t, and 0. I always line these things up just like this because then they're ready to go for the cross product step. If you need the mnemonic, you can put I, J, and K up in there. The I component is going to be 0 because we blot this out and we do this little determinant, and this column of zeros wipes out the whole I component. Similarly, the J component, we blot out this column, we have this, and the zeros blot out the J component, and we're left solely with a K component. That makes sense, right? Because this is a plane curve. It sits in the xy plane. So the cross product is going to point in the z direction. So let's do the z component. We blot out the column of zeros. We get 25 sine squared plus 25 cosine squared, which works out to just be 25 because of another friendly Pythagorean identity. They're everywhere, folks. Now we need the magnitude of r prime. And the magnitude of r prime is just the length of this vector, which is 25. We also need the magnitude of r prime, all the pieces. The magnitude of r prime is the square root of 25 sine squared plus 25 cosine squared, yet another Pythagorean identity. And that's going to work out to be 5. Taking all these various bits and plugging them in, we have 25. Don't forget, this is the magnitude of r prime cubed, so it's 5 cubed. This is 5 squared over 5 cubed, which is just 1 over 5, and the curvature is 1 over 5. We could have guessed this without doing any of the work, because this is a circle of radius 5. And we know that curvature is inversely related to the radius. But it's nice to have that confirmation. Actually, I'm going to do one more thing here because I didn't give a specific exercise for this. Let's find the arc length function associated with this particular curve, starting at 0 and going up to t, and integrating r prime du. Sorry, magnitude of r prime du. We computed the magnitude of r prime already as 5, so the arc length function, starting from 0 going up to t, is just 5 du. Integrating 5 with respect to u, we get 5u, and we want to evaluate from 0 to t. Plugging in t and plugging in 0 and subtracting, we get 5t. So the arc length function for this space curve is just 5t. S equals 5t. If we wanted to reparameterize this circle, to reparameterize, by arc length, we simply solve for t, and we get t equals s over 5. My s's and my 5's are very hard to distinguish. I apologize for that. And then substitute into the original curve. So then we get r of s is, replace the t's with s over 5, and we get 5 cosine s over 5, trying to really make my s's and 5's distinct. And then we have a 5 in the middle, and then, what is it? 5 sine s over 5, like that. So many 5's and s's. And that would be an arc length parameterization. So for example, if I'm sitting on the curve and I go a distance s from my, I go a distance 0 from my starting point. Here's my starting point, say right here. I go distance, I'm not anywhere. Now, what's the circumference of this circle? We know that the circumference is given by 2 pi r, not the r of our space curve, but the radius, capital R. So in this case, the circumference is 2 pi times 5, aka 10 pi. All right, where are we if we go halfway? Like, how do I tell somebody to get over to, say, this point? Well, I tell them to travel a distance 5 pi along the circle. So here, go 5 pi units along the circle. Well, how do I find that location using my arc length function? I compute r of 5 pi, and I get 5 cosine. All right, cosine of 5 pi over 5, right, because that's s, 5, and then finally 5 sine 5 pi over 5, like that. Now, what's 5 pi over 5? It's just cosine of, it's cosine of pi, which is -1, so we're -5. And then we have a 5 here in the middle, and then we have a 5 times 0 in the last slot. So where are we? We're sitting out here at, I guess I should be really careful here to note that this is the circle in, where does the circle live? It lives in the ij plane. Oh, and actually I made a little typo here. Excuse me. And we don't need this, we don't need this, this, that. Okay, we're good now. 5 and 0. Okay. And we're sitting out here at -5, 0. So we can see how this arc length parameterization is consistent with the idea of circumference of a circle. So go this far along the circle, that's where you're going to be, and that's how we locate ourselves on this space curve. Last exercise, we're going to talk about osculating circles of an ellipse given by this equation. Because I know that osculating circles and planes involve working with, sorry, not planes, just oscillating circles involve working with curvature, I'm going to rewrite this curve in terms of a space curve. So if we write this in standard form, we see that this is really x squared over 2 squared plus y squared over 3 squared equals 1. That's the ellipse in standard form. Once I see that the major axis goes along y and the minor axis goes along x, and we can write a parameterization of this ellipse as 2 cosine t, 3 sine t, and if we want to really be pedantic, we'll say that its z component is 0, meaning it's sitting in the xy plane. Okay, if I want to find the osculating circles of this ellipse at these various points, let me sketch this ellipse for you. Okay, so we're going out 2 units. Yeah, we got 2 units in the x direction and 3 units in the y direction. And we sketch the ellipse. It looks something like this. And we are interested in this point and this point, 2, 0 and 0, 3. And we want the osculating circles at those 2 points. Well, remember that the radius of the osculating circle is the curvature at that point. Sorry, 1 over the curvature at that point. So we're going to have to compute kappa, and I'll remind you that that's r prime cross r double prime over the magnitude of r prime cubed. And we now go through and compute the pieces in sort of the organized way that I outlined earlier. R prime is going to be negative 2 sine t, 3 cosine t, and 0. R double prime is going to be negative 2 cosine t, negative 3 sine t, and 0. R prime cross R double prime is going to be 0, 0, and then the last component is going to be negative 6 sine squared, 6 sine squared minus 6 cosine squared, aka 6. The magnitude of r prime cross r double prime is simply 6. The magnitude of r prime, which we also need, is this bit up here, 4 sine squared t plus 9 cosine squared t square root. Now note, again, not a Pythagorean identity here. You're stuck with this complicated magnitude. But given that magnitude, we can now quickly compute the curvature as 6 over the quantity 4 sine squared t plus 9 cosine squared t to the 3/2. And you might say, hey, where did that 3/2 come from? Well, I've got a 1/2 here, and I've cubed it. So that comes together as 3/2 in the exponent. This is kappa as a function of time. Now, we're interested in knowing kappa here and here. So we first have to figure out what time corresponds to this point and what time corresponds to this point. Well, when t equals 0, we're clearly at the point 2, 0, so this is t equals 0. And when t is equal to pi over 2, we're up here at this point. How do I know that? I know that by guessing and plugging in those t values and hoping that they match up with the coordinate values that I expect at those 2 red locations. So let's do the osculating circle at t equals 0. At t equals 0. What's kappa there? Kappa of 0. We plug 0 in for t here, and we get 6 over, that's 0, that's 9, we get 6 over 9 to the 3 halves. 9 to the 3 halves is really just 3 cubed, so that's 3 cubed. That's 2 over 3 squared, or 2/9. And so the radius is 9/2. Okay, so we know that the radius of this osculating circle is 2.5. So the center, where's the center of the osculating circle? Now we have to bring to bear our knowledge of the unit tangent vector and the unit normal vector. Which way is the unit tangent vector pointing at this point t equals 0? I'll sketch it in there, maybe as green. It's pointing in this direction. And we know that the unit normal vector therefore points in this direction. And therefore the center of the circle lies somewhere off in this direction. We don't know where, but it's in that direction. And we kind of do know where. We know that it's 2 units, 1, 2.5 units in the normal direction. So that's the center of the osculating circle. What is that in terms of coordinates? It looks like it's minus what? Minus 1/2 and 0. So the center, and you might want to go through that again to convince yourself of the reasoning. The center is at minus 1/2 and 0. And if we're to sketch that circle, it's a big circle, right? It's not that big. It's a circle like that, kind of, that just kisses the ellipse at the point 2, 0. We're asked to find the equations of the osculating circles. Given the center, given the radius, the equation is simply x plus 1/2 squared plus y squared equals 9/2 squared. Okay, wouldn't be a lesson without a bit of a visualization, so let's go over and confirm that this is the osculating circle by looking at a visualization in GeoGebra. This is a 2D problem mostly, even though we've tacked on that extra z coordinate for the cross product. So we'll run the 2D version of the graphing calculator in GeoGebra, and let's first get our hands on the ellipse. The equation of the ellipse, not parametrically, in rectangular coordinates is 4y squared plus 9y squared equals 36. There's the ellipse, and there's the 2 points 2, 0, and 0, 3 that we're asked to find osculating circles for. So that's the base curve. The osculating circle has this equation. The osculating circle at 2, 0 is x plus 1/2 quantity squared plus y squared equals 9/2 squared. And it looks like I've got a typo in here, maybe. Let me just double check. Let me pause while I do that. Okay, not a typo. Mistake. One of the reasons it's nice to sort of come at a problem from lots of different angles. Probably if you were following along, you noticed this. 9/2 is not 2.5, it's actually 5.5. 5.5. So we've got to go back 5.5 units from this point. So that's 1, 2, 3, 4, 5.5. 5.5 units. That changes the That changes the center to be minus, oh good lord, 2 minus 9 halves. That's going to be 4 halves minus 9 halves is minus 5 halves. That's where we are, so we've got minus 5 halves here. And everything else should be okay, so we just need to tweak the equation of the circle that we put into GeoGebra here. Change that 1 to a 5. And let's hit enter, and that looks good. Let me just, for emphasis, put the point to 0 in there. And we really begin to see how well the osculating circle, which is quite large relative to the base curve, how well it approximates. Look how well it approximates the ellipse near the point A. They're indistinguishable near the point A. Similarly, I actually went through and computed the osculating circle for the point 0.03, and let me dump that in there for you. So you don't, this would be something that you can verify. I found that the curvature there, well, let me just write it out here. You can check on your own. At 0.3, I get curvature of 3/4. Therefore, the radius is 4/3, and the center is going to be 0 and 5/3. And if we plot that, well, let me give you an equation first. So that's x squared plus y squared minus 5/3. Sorry, not y squared. Y minus 5/3 quantity squared equals 4/3 squared. If we drop that equation on the GeoGebra sketch, x squared plus quantity y minus 5/3 equals 4/3 quantity squared. We see the oscillating circle up here at the point 0.3. Okay, and we do again see that the osculating circle does a nice job of approximating the curve at that point. Okay, that's a lot. You're going to have to spend a little bit of time on this. I'm going to ask you to look at all of the exercises and do a sampling of them to familiarize yourself with these various concepts. And when you're finished, head over to WebWork and do the assessment for Chapter 3, Section 3. Thanks.